Hello everyone and welcome back. In this video, we're going to take a deep dive into a robust SEPIC DC-DC converter model built in Simulink. For engineering students, this is the perfect example of how to bridge theoretical power electronics with practical closed-loop control and advanced battery modeling. We'll look at the power stage, the control loop, and a custom state-of-charge battery model implemented via a MATLAB function. Before we look at the components, let's understand the big picture. We have a battery supplying power to a SEPIC converter. The goal of this system is to regulate the output voltage to a steady 60 volts across an 85-ohm load, regardless of the battery's state of charge or load variations. The SEPIC topology was chosen because it is inherently a buck-boost converter. It can step up or step down the input voltage to maintain that steady 60-volt output. Let's start on the far left with the battery block. This isn't a standard Simulink battery block. Instead, it is a custom MATLAB function called battery_model_full. Inside this code, the students will see a modified Shepherd equation used to model the battery's voltage. It uses a nominal capacity of 13.9 amp-hours, an initial state of charge of 90%, and an internal resistance of 57.6 milliohms. A very important aspect of this model is that it handles both discharge and charge states separately. For discharge, the voltage equation uses a straightforward model, while the charge phase introduces a denominator adjustment to handle the charging dynamics correctly. The battery function outputs two main things: the actual battery voltage, which supplies the power stage, and the state of charge, which lets us monitor the battery drain. Now, let's move into the power stage of the SEPIC converter. We start with the battery source, which feeds into the primary inductor, labeled L1, rated at 1.4 millihenries. Next, we have the power MOSFET switch. The turning on and off of this switch dictates the energy transfer. When the switch is closed, energy is stored in L1, and when it opens, that energy is transferred. The capacitor, C1, is the coupling capacitor, rated at 10 microfarads. It acts to transfer energy between the input and the output sections. Following that is the diode, which allows current to flow to the output only when the MOSFET is off. On the secondary side, we have a second inductor, L2, also 1.4 millihenries, which acts as an output filter inductor. Finally, the output capacitor, C2, rated at 220 microfarads, smooths out the voltage spikes to provide a clean DC voltage to our 85-ohm resistive load. To automatically maintain our 60-volt target, we need a feedback control system, which is located at the bottom of the screen. Here is how it works. First, a voltage sensor measures the actual output voltage across the load. This measured value is fed back and subtracted from our reference value of 60 using a summing junction. Notice the butter block. This is a second-order Butterworth low-pass analog filter. Why do we need it? The SEPIC converter operates at a high switching frequency, which introduces high-frequency noise into the voltage reading. This filter removes that noise to give the controller a clean signal. The filtered error signal then goes into a discrete PI, or proportional integral, controller. The PI controller computes the necessary duty cycle to minimize the error. Finally, the output of the PI controller goes into a PWM, or pulse width modulation, generator. This converts the continuous duty cycle into the gate driving signals for the MOSFET. Here we have the scope plot for our closed-loop SEPIC converter simulation. Let's break down what's happening with our output current and voltage from the moment the simulation starts at time 0, up to 1 second. Looking at the bottom trace, this is our output voltage. We are trying to control this to a steady reference of 60 volts. However, this graph teaches us an incredibly important lesson about poorly tuned closed-loop controls, particularly integrator windup. At time 0, the controller sees an error of 60 volts, so it immediately commands a very high duty cycle. This causes a massive, and I mean massive, initial overshoot. The voltage spikes right up past 250 volts. The system then fights to compensate, dropping the duty cycle dramatically, causing the voltage to crash downwards into an undershoot of roughly 45 volts. From there, the PI controller slowly and painfully integrates the error back to 0. You can see it takes about half a second, 0.5 seconds, for the voltage to slowly creep back up, and it only finally settles onto the 60-volt set point just before the 1-second mark. Now look at the top trace, which represents the output current flowing through the 85-ohm load resistor. What you'll notice is that it perfectly mirrors the shape of the voltage plot because of Ohm's law. Because the load is purely resistive, the current is directly proportional to the voltage. So we start with a massive current spike of over 2 amps, which corresponds directly to that 250-volt voltage spike. It then dips to roughly 0.35 amps during the voltage undershoot. Finally, as the voltage settles back to its target, the current slowly rises and asymptotically stabilizes. And if we look closely at that final steady state, the current lands at approximately 0.7 amps. Let's do the math. 60 volts divided by 85 ohms equals exactly 0.705 amps. Our math and our simulation match perfectly. In summary, this Simulink model is an excellent educational tool for studying DC-DC converters and feedback control. By separating the battery model, the power stage, and the control logic, students can visualize how each component interacts to maintain system stability. If you want to test this further, try adjusting the PI gains to see how the system's transient response changes, or change the load resistor to test the robustness of the controller. Thank you for watching, and I'll see you in the next one.